recording. Has anyone else joined us?
No, I don't think so.
Okay, digital electronics. We looked at the comparison between analog electronics and digital. Analog signals can take any value between two limits, e.g. 4 to 20 milliamps, 0 to 10. So they can be any one of the infinite number of values you can specify between those two limits. Whereas digital signals at the lowest, most basic level can only be one of two states, i.e. 0 or 5 volts, 0 or 10 volts, i.e. they can only be on or off. Okay, are you happy with that? You done, Taylor?
Yes, thank you, Mike.
Yeah, okay. All right, so what we're going to do in a little while is look at some specific logic gates. Yeah, but what logic gates do is they use transistors as switches to turn outputs on and off. Okay. Two main families of logic gates. TTL, which stands for transistor logic, and they use NPN and PNP, BJT transistors. So they come in packages of a number of gates, but their function is achieved using NPN and PNP bipolar junction transistors. And then you got CMOS, which stands for, find it here, complementary metal oxide silicon. And these use MOSFET.
Hi, Dom.
Hi, Dom.
Hello. I've had to use my phone.
Okay, Dom. Well, at least you're with us anyway. Yeah.
Emotionally.
What? Hang on, just let me put the recording off for a minute, Dom. What messages were you getting when you tried to join? That's all right. So just to summarize there for the video, I'll summarize this page as well because I don't think I was recording on that. You've got different voltage levels accepted for logic 1 and logic O for inputs. Inputs, logic O is up to between 0 and 0.8 volts. And logic 1 is between 2 volts and 5. And then for your output, logic 0 is between 0 and 0.4 volts. And logic 1 is between 2.7 and 5. If you allow signals to fall into these indeterminate regions, you have no idea of what is going to be recognized as. It could be recognized as 0 or 1, dependent upon the exact level that it is. To summarize the different voltage levels used for the two different types of circuitry, TTL and CMOS, TTL logic at 0 is between 0 and 0.8 volts, and logic 1 is 2 to 5 volts, and CMOS logic 0 is 0 to 1.5 volts, and logic 1 is 3 to 18 volts. Okay, guys?
Yeah.
Goody, goody. Right. So we're going to start now to have a look at some different logic gates. We're going to look at AND gates.
OR gates.
Yeah, OR gates.
Not.
NAND gates. Yeah, actually you would normally put that in between there. You'd look at the NOT gate.
Yeah, boy.
The NAND gate. Or the NOR gate. Exclusive OR gate. You might find time for the exclusive NOR gate. Yep. So we're going to have a look at those and look at something called truth tables in terms of the basic gates. Yep.
Oh. Upcoming event, mad one with the boys.
The festival.
Yeah.
I'll tell you what, I turned notifications off. I put it on silent mode and still it keeps flashing up with these.
Silent and
notifications.
off is two different things. You need to put on it do not disturb.
Yeah, I've got do not disturb on all the time, and that's still flashing up.
That's well annoying.
Yeah, it is. Right, AND gate. Symbol. Yep.
Yeah. I'm a pearl flexing on him.
Boolean expression for that is that Q, the output, is equal to I dot B. So dot is used for AND. Yeah. That means A and B. And then we have a truth table. What you do with the truth table is for all values, possible values of the inputs, you say what the value of the output should be. So we have two inputs, B and A. They're always done in that order, so the highest bit to the left. Q, a truth table. Then we can fill it in with the end of a color, blue. So we have B off and A off, on, off, and both on. Yeah. So for this, for the output Q to be on in an AND gate, the only case is when both B and A are turned on. So that's the only logic high we get, and the other two.
Gotcha.
Yeah.
Yeah.
So the truth table for an AND gate is that we need both inputs on to get the output on. Okay. Now, it's also possible to have three input AND gates, so A, B, and C. It's also possible to have four input AND gates, A, B, C, and D. Yeah, and again, for both of that, so for the three input AND gate, you'd need all three inputs to be turned on to get a logic high out. And for the four input AND gate, you'd need all four to be high to get a logic one out. Okay?
Yeah.
Yep. And that's the same. That's the function of the AND gate is exactly the same, whether we're talking about one from the CMOS or one from the TTL. Yep.
Yeah.
Okay.
Yeah.
The other thing that we can do is if we want an AND gate with lots and lots of inputs, we can actually cascade them. So if we wanted a 6 input AND gate, we can go A, B, C, D, E, F. So to get any one of those to come on, we would need both the inputs to be on to get any one of the outputs. If we then feed all those three outputs into a 3 input AND gate, we then add, and so then we've got to have all these three at logic 1 to get a logic 1 there, and to do that we must have all of these turned on. So that circuit there, with Q being there, this is A and B, this is C and D, this signal is E and F. So what we have there is Q is equal to A and B and C and D and E and F. So we would need all of those to be on to turn that Q on. Yeah. All happy with that? All understand?
Yeah. Well,
All right. Just to give you an example of what you can get in TTL, for instance, a 74 LS08 is a quad two input. So what that if you buy that chip, the 74 LS08, you get 4 2-input AND gates on that chip. Yeah, a 74 LS 11 is a triple input. It's a triple, sorry, 3-input. So you get 3 3-input AND gates, and then a 74 LS21 is a dual 4-input. So there's 2 4-input AND gates on there. All 3 of them come on 14-pin chips. 14-pin chips. Just an example, I won't give you the numbers on all of them because there's no need for you to remember them or do anything like that. If you wanted one, you just look them up. But just to give you an example, that they come on 14-pin chips, and you can buy a quad 2-input, a triple 3-input, or a dual 4-input chip. All right?
yeah.
So that's AND gates. You're all happy with that?
I'm happy.
Good. Nobody else is answering me. You don't like talking to me.
Yeah. Very sided, this, Mike, isn't it?
It's what?
Very two-sided.
Right. Next. OR gate.
Yeah, boy.
Yep. The OR gate has a symbol that looks like
The
this.
arrow-looking one. I'm a pillar flexing on like
Q. Input. I. B. Yep. Q equals I plus B. So in Boolean algebra, plus is OR. Yep. Okay. And then the truth table. B, I, Q. 0, 0, 0, 1, 1, 0, 1, 1. And we get Q high if one or the other or both are on. So the output line for an OR gate is 0, 1, 1, 1. Any one in gives a 1 out. Yeah. Okay.
A-okay.
So if we had a circuit where we got two switches, and you wanted to turn on a lamp with any one of those two switches, you could put an OR gate in. And now it needs more circuitry, but any one of those two being turned on would turn that lamp on. Yep. Again, you can get 3 input. Yeah. So with an OR gate, there's only one way you can have no output, and that is when all the inputs are logic low or 0. Yep. All happy?
Oh, yeah.
I'm sure you'll shout if not. Okay. And again, we can use multiple gates to make up larger numbers of inputs if we wish to. Yep. Right. Going to move on now then to the logic NOT gate. The symbol is, it's only got one input, A. It's a triangle. And it's got a little open ball on the end. And then the output Q. It's called an inverter or NOT gate. And not what it basically means is the output is not the input. So whatever you put on the input, you get the opposite on the output. Yeah. So the truth table for a NOT gate is when I is equal to 0, Q is equal to 1. When I is equal to 1, Q is equal to 0. Yeah. So it simply inverts whatever signal is being input to it.
Got it.
Okay. And these come in four or 6 NOT gates on a chip. The other thing you can do, we'll talk about it when I do the NAND and NOR gates in a minute, but you can make, and there's a good reasons why you'd want to, you can easily make a NOT gate out of a NOR or a NAND gate. Yeah. Okay.
Mix them up. Nice.
Well, it's not about mixing them up. It's about economy of what you buy to to stock on an economy of chips that you put on your circuit board. We'll talk about that a bit later, or maybe in next week. Okay.
Yeah.
So Boolean wise, Q equals not I, and what we say is Q is equal to I bar. We put a bar over the top. That means Q is not A. Yeah.
Yeah.
That be the NOT gate. Okay. Right. Nand. Try and symbol. Still got, as at basic level, two inputs, A and B. The symbol is like an AND gate, but it's got the ball on the outside to say the output's inverted. And there's your output Q. Yeah. So this means not and. Yeah.
Yeah.
Boolean expression because we've got our I and B. That's what we would have. Q is for an AND gate, inverted. Yeah. So we put a line over both of them to say it's an AND gate with the output inverted. Truth table is B, I, we go 00, 01, 10, 11, and the Q is exactly opposite to what you would have for an AND gate. So the AND gate output goes 0, 0, 0, 1. So the NAND gate output goes 1, 1, 1, 0. Yeah. So that one is the NAND. That's the AND. Just to show you that whether it's the AND gate with the output inverted. Yeah. Again, we can get 3 inputs and we can chain them together. Okay. Also, what we can do is this. So there's an AND gate. Join these two together and we've got a NOT gate. So if you think about it, if you're putting 4 or 5 NAND chips on your circuit board, chances are you might have some spare NAND gates, and you can turn them into inverters rather than buying and fitting on your board separate NOT gate chips. Yeah.
Yeah.
All right. Just want to mention one thing that you don't do with logic gates. If we had a on our circuit board a 4-input AND gate like this, yeah, and we only wanted we got a spare 4 input, but we only want 3 inputs. What we can do is join these two together and make a 3-input AND gate. What I was going to explain to you is it's bad practice to leave input terminals floating in logic circuits. So although you'd get the same, well, with the AND gate, you wouldn't get the same function. You need to tie that up here so that you actually, if you get a 1 on there and on there and on there, you get a 1 output. But you must never leave input terminals floating. Because if we take an OR gate multi-input, yeah, 1, 2, 3, 4, you might think, well, as long as I got these 3 connected, I'll get my normal OR function. But if you leave this one here floating, you could get a bad outcome. So you tie them together, any loose ones. All right?
Yeah.
Okay, so the NAND function is covered. We'll do one more and then we'll have a quick break for a brew.
Sounds good.
Right, NOR gate. So, symbol for an OR gate is, we draw the OR gate, inverting ball on the front, Q, I, and B. Yeah. So that's the symbol. A Boolean expression is Q is equal to I or B with the output inverted. Truth table. B, I, Q. 0, 1, 1, 0. 0, 0, sorry. 0, 1. 1, 0, 1, 1. And the output is opposite to what you'd get for an OR gate. So in an OR gate, all these three would be on. So in a not OR gate, they'll be 0, and the top one will be 1. So it's exact inverted OR gate. Yeah. Any one in will give you a 0 out. Okay. And again, you can get 3 input NOR gates and 4 input NOR, make a 4 input NOR gate out of a number of NOR gates chained together. Okay. Yeah.
Yeah.
Right. Well, okay. What we'll do now is we'll take a short break, and I will catch up with you again at 10:02. All right, is that fair?
Sounds good.
Yeah, lovely.
Yeah.
Good. Good. See you then.
Bye.
Yeah.
Right. The exclusive OR XOR gate. Yeah. Symbol. Looks like this. I and B input. It's like an OR gate symbol with another line on the back, like so, and a Q output.
You should critically analyze.
Boolean expression is Q is equal to I, and then we have a plus symbol in a circle for exclusive OR. Truth table. B, I, and Q. And what we get is what we get with the OR. So it's A or B, but not both. So both low means we get a low output. If A is on its own, we get a 1. If B is on its own, we get a 1. But if they're both on, we get logic 0. So it's OR, but it's exclusively OR and not including the AND. Yep. Okay.
All good.
Yeah. And then lastly, I think that's the last one that I said we was going to do. Exclusive NOR, XNOR, so the symbol is the exclusive OR symbol with the inverting ball on the front. Boolean expression is that Q is equal to A exclusive or B, the output inverted. So bar across the top. And the truth table has B, A, and Q. Has the exact opposite, the inversion of the exclusive OR. So where the exclusive OR had any one in, gave you a 1 out. This is any one in. Those two are there, and we get the AND and no AND. So that's the exclusive OR. Yep. Okay.
All good.
Yeah. Good. Right. So they are the basic logic gates that you can come across in logic circuits. Yeah. So then you can use them together in what's called combinational logic to handle more complex functions. So we'll take a look at something like that now. Yeah.
Nice.
So combinational logic. Three main ways of specifying combinational logic. These are: 1, Boolean algebra. 2, truth table. 'Defines state of outputs for all possible input combinations. I'll show you what I mean by that in a minute. The truth table is something that we're going to look at more closely, perhaps not so much the Boolean algebra and logic diagram. Graphical representation. Of each gate. Yep. So if we've got a more complex logic circuit, we can express that in any one of those 3 ways. Yep. So, by way of an example, everyone up with that? Okay.
So far, so good.
No,
Not there yet, Taylor?
just a little bit left.
Okay, go on. Yep. There now?
Yep.
Okay. So if we take these three representations, so if we've got three inputs A, B, and C, A and B into a Nand Gate, C directly into an AND gate, Q being the output. That also feeding into the AND gate, and then I and B going into a NOR gate, like so. Yeah. Now, if we start to think about Boolean expressions that we could put onto this diagram, so I'll do them in red. This output here on the NAND gate would be A and B inverted. Yeah. And this line here is just a straight C. And this line here is A or B inverted. Everybody understand that?
Mostly.
Yeah. And therefore, Q is equal to A and B and A or B inverted and C. Yep, that would be the full expression because this AND gate is AND and these other three together. And a truth table for that we got C, B, and A as our possible three inputs, and they could be I missed one. Yeah, 1 1 0 1 1 1 should be 8 because we got 3 inputs. There must be 8 combinations. Yeah, 2 to the power 3. Okay, and then Q for that truth table. You get O, 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 1, i.e. the only way to turn that output on is if C is on, B is off, and A is off. Yeah. Okay. So if we look at that line there, what we're saying is, will the output be on if this is on? This is at logic 1, and this is at logic 0, and this is at logic 0, right? What's the output of a Nand gate and both the inputs are logic 0? Well, Nand gate is 1110. Yeah. So if they're both 0, we've got a 1 out there. So that's at 1 in the current state. C is on, so that's at 1. And then we got here, we got both of these off. So a NOR gate is the opposite of an OR, so it's that. So we got both zeros on there, gives us a 1 out. Yep. And then the 3 input at NAND, you'll get a 1 out unless they're all off. And so we get a 1, right? The idea is really not necessarily for you to understand that circuit in particular, but to understand that it can be expressed in 3 different ways. The truth table, the Boolean expression, and the logic diagram. Yeah? Okay?
Understood.
All right. So, what I want to do with you now is show you how we can use logic circuit to make a combinational output of a function. So if we're going to put logic gate logic gate motor start stop. I don't know how many of you are familiar with motor start stop circuit, but the control side of it, in normal switching sense, you'd wire this so that if that's 12 volts and over here is 0 volts, you'd have a relay. Yeah, you want to turn that on. We'll call that Q, and no reason I'll call that Q will be obvious soon. What we want to do is use a traditional push button to to turn that motor on. So that would energize that relay or contactor and start the motor. So we call that start. And then what we want to do is we don't want to push the button, the motor start, and then when we let it go, it stops. So we put a normally open on Q in there as a latch. Yep. Then when we push that button, Q will energize, close this off, and keep the motor running. All understand that, yeah?
I'm trying to, I need my card.
But then what we need is a way of stopping it. So what we have is a normally closed push button that is the stop switch. Yeah. So if you think about that circuit, when we push the start button here, we close this circuit, current flows through that closed stop button and turns that on, yeah, which closes this and completes that circuit. So when you take your finger off the start switch, the motor carries on running. But when you push the stop button, you break this circuit here and you turn the motor off. Do you all understand that?
Yeah.
Yeah. Okay. So I'm going to try and build that in logic gates. So here's our first of all, we're going to implement this bit here. What kind of gate do I need to implement those two switches? Think about the motor runs if in terms of start and Q. The motor runs if
Q is closed.
Yeah, if Q is closed.
And start.
And the start. Do we need them both?
One or the other.
Yeah, it's or because they're in parallel. It's one or the other. Yeah. So we can start here with an OR gate. We can connect into that. Start. Right, and we're going to get Q. I'm going to label that Q. We're going to get that from the output at the other end. Yeah. So what we're saying is, if we've got start or Q, we're going to get an output here. Yeah. So we've implemented up to here. What do we need to implement the stop button? Think about it in terms of we want the motor to run if we've got Q or start, and what in terms of stop. Remembering that the stop button in its normal state is closed. Logic 1. we need to and with a stop button. Yeah.
Right.
So here's our stop button. Going to add it. Yeah. I'll do that better on that. Okay. So we
Okay.
have to have either start or stop, start or queue, and then what we need to do is link this queue back round to the front. I could have drawn that better on that. Right, boys, just stop drawing for a minute. It's horrible. Right, here's our two gates. Now we know what we want. There's the OR gate. There's the AND gate. There's Q. Feed that back into there. Feed the start button in there. And the stop button in there. Yep. Okay.
Yeah.
So in terms of does this circuit do the job we intended it? I changed to red. Okay. If we push the start button, yeah, this will go to 1, and that's an OR gate, so that'll go to 1. And this is already 1 because that's a normally closed. So we'll have a 1 on there. We'll get a 1 out there, which will put a 1 on there. Do you all follow that? So initially, we only need a single push of that start button to get a logic 1 on the output of the OR gate. There's a logic 1 on the second input of the AND gate because we normally close stop button. So we've made the AND, we get a 1 out the end, feedbacks into that Q input on the OR gate. So when we let go of the start button, we've still got a 1 here at the output of the OR. We've still got the AND, so the motor carries on running. Yeah, motor. However, if we push the stop button in while the motor's running, that goes to logic 0, as does that, and therefore we haven't got the AND. This goes to logic 0 and breaks the latch, so the motor turns off. Yeah? All happy with that? Or not?
Happy, I guess.
Aye or nay? Yeah.
Yay.
Right. Let me see if I can dream something up for you to have a go at. I've done nearly all the work this afternoon. Right. Two valves, A and B, must be on before switch C can start switch C or D. So there's two switches can start a pump. Yeah. So we've got 4 inputs. Yeah. And we got 3 outputs essentially, because we've got the inputs are A, B, C, and D. So A and B are the 2 valve limit switches, if you like, that are going to check that the valves are open. And then we're only going to have one output, the pump. Yeah. So this circuit is going to check these 2 switches, yeah, to see if they're turned on. And then if they are, you can turn the pump on with either switch C or switch D. So think of it as the 2 ends of the production line, and you can start the pump from either end as long as the 2 valves are open. So the combinations we got here is all off. Going to run out of space. Go over here. Should be 16. 1, 2, 3, 4, 5, 6, 7, 8. 16. Yeah. Okay. Now, anywhere where we've got a 0 in the 2 valve limit switches, we can't have an output. So any 0 in these 2 lines mean we get a 0 at the output. So none of those lines are any good. Yeah. Let's start to simplify a little bit. When we've got both here, both valves open, that would still be off because nobody's turning the pump on. But any one of these will turn the pump on. Can you come up with a logic circuit that will turn on if we have any one of these three input states? Want to have a go at that? 10 minutes?
Can give it a try.
Good. I'll pause the video. Have a go, 10 minutes. See if you can come up with the logic gates that will do that function. Recording. So we've got 4 inputs, A, B, C, and D. A and B are the 2 valve limit switches, so they're checking that the valves are open. And the specification says that both valves must be open before you can turn the pump on. Yep. So we must have A and B. It's the first thing we must have. So an AND gate will do that. We've got A and B. Agreed?
Oh yeah.
So we've got to have those 2, and then we've got to have either of C or D being turned on to start the pump. So C, D, into an OR gate. Yeah. And then we bring those 2 together in another AND gate. And there's our Q, which is our pump. Yep. So on this line here, we've got C or D. Yeah. And overall, Q is equal to A and B and C or D. Yep. And if we think about it still further, does it do the function we said? Well, if this one is 1 and that one is 0, we'll get 0 over there. That'll be 0, and therefore you won't start the pump, whatever you do with the switches. Yeah. We need both of these inputs to be logic 1, so that we get a logic 1 out there and a logic 1 into the AND gate. That means both valves are open, and that's ready for the pump to be started. So then if somebody pushes either C or D or both of them, you get a logic 1 there, and the pump turns on. So although that looked like, when you looked at it here and looked at the full truth table, it looked right. Actually, because we need both A and B, it rules out a lot of combinations. We only got 4 left to deal with. Yeah. Okay.
Yeah.
Happy with that?
Happy as I'll ever be.
Right. Okay. Well, I think that'll do us for today, and we'll pick up again on session next week. Okay. What I will just have a chat with you about is this thing about the assignments, and I think Omar was going to talk to you later as well. We had a meeting before this session, me and Omar and Adrian. And what we decided is, bearing in mind the situation, is that we're going to keep the issue dates as Omar already published. Yeah. So you've already got the project assignment anyway. But the materials, the maths, and the electrical principles will be issued on the dates he put in his original email. I'm sure he'll email you again anyway. The dates for the draft hand-ins, which the intention there is that when we introduce the assignment to you, we will give a verbal indication of which parts cover the pass criteria. I don't know if you picked that up from Omar or from Adrian. The idea there is that you'll hand in a draft after 2 weeks, so that will stay, the draft hand-ins will stay as already published. The idea being, we'll comment back and you should have a pass or know what you've got to do to get at least a pass. So that's not normal, as you know. You're not normally meant to do that. But what we have decided to do is give you 1 extra week on all of those 3 deadlines. So the project hand-in will stay as is because you've already had 2 weeks on that anyway. But we'll add another week to the materials, the maths, and the electrical principles hand-in. So that will take the materials hand-in to the 16th, the maths hand-in to the 23rd, and the electrical principles hand-in to the 30th of June.
23rd of June.
Okay.
Perfect, thank you.
So that's just adding 1 week onto those 3 deadlines from Omar's original email he sent to you. We can't go any further than that because we need to be finished before summer holidays and things for us. So
We discussed with Adrian about possibly going into it.
yeah, I know you did. And we discussed it and decided that that's not something we think we can do.
I know, but this was happening about 2 hours ago. And
What's that?
our discussion about going into the summer holiday.
Yeah, I know
for
it
the
was.
assignments.